Okay, this is just a little bit about the applications of rational expressions. The two applications that we're going to be concerned with will be the time together, time alone kind of application. So here's the big formula for that kind of idea. Time together over time alone, added with time together over time alone equals to one whole job done. And then the other big idea we're working with is distance equaling rate times time. And then knowing that there are two other ways of writing that formula based on what you're given. So the time together, time alone problems are more like people painting a room together, stuff like that. Distance, rate, and time, you're going to see that in the context of perhaps a plane flying with or against the wind, a boat traveling downstream or upstream, things like that. So let's try out one of the distance, rate, and time ones here for the moment. This comes from the homework exercises. So here we have that Casey can travel 8 miles upstream in the same time it takes her to travel 12 miles downstream. So just kind of right away I'll look out for my numbers. The other key thing we have so far is it takes the same time to go up as it does to go down. We also know her boat travels 15 miles per hour in still water. What is the rate of the current? Okay, so this one's started as far as the setup goes. I'm going to organize it in a chart, just like we talked about in class, and then from that we'll be able to build the equation. So as far as distances go, the way this chart's already been set up, I have to be a little careful. My distance upstream was 8. My distance downstream was 12. And we talked about letting the variable just stand for what you're solving for. So in this case, we're asked about the rate of the current, so x is going to be used to represent the rate of the current. And that's already happening down in our little box set up below, so we'll just be consistent. And here, if we know that the boat travels 15 miles per hour in still water, when it travels upstream, the current will slow it down. So that's why we see 15 minus x for the rate upstream. Kind of the flip side of that is if you're going downstream, it will be the speed of the boat in still water plus the speed of the current. So going downstream, the current makes the boat go faster. And now the last part to fill in our box before we consider our equation is thinking about time. So if I float back to our first page for just a second, I want to talk about this relationship right here, which is that time is the same as distance over rate. So if we manipulate our kind of classic d equals rt, distance equals rate times time formula, and solve it for time, we get that time is distance over rate. Keeping that in mind, a nice way to finish filling in our little box here is to just express the time category as the distance over the rate. So for downstream, distance was 12 and rate was 15 plus x. And for upstream, distance was 8 and time was 15 minus x. Okay, so that is our setup in the box. Now when we go to write the equation, I'm going to go back to our original problem one more time. So again, we had Casey traveling 8 miles upstream. Okay, we've accounted for that. In the same time, I still haven't used that. It takes her to travel 12 miles downstream. Her boat travels 15 miles in still water. What is the rate of the current? So I've really utilized everything I was given except for the fact that it takes the same time to go down as it does to go up. So my equation will simply be setting these two times that we have down here in our box, setting these equal to each other and solving. So let's go ahead and do that now. And I'll just get a little bit more room. So if I set those two times equal to each other, my equation is basically just going to say that 12 over 15 plus x is equal to 8 over 15 minus x. Alright, and then I'm just going to go ahead and solve this using the same method we saw back in section, the earlier section on solving. So that idea was find your LCD and bring both fractions, in this case, up to the LCD. So it looks like my LCD will be the product of the two denominators we have. We need a 15 plus x and a 15 minus x. So we'll go through those steps of bringing each fraction up to having the LCD. And then the nice part is the common denominators will cancel out. So just making a little bit of room for that to happen. I can see here that my first fraction has the 15 plus x, so introduce the 15 minus x. And on the other side, we have the minus, so we need the plus piece. Okay, so that's looking good. At this point, we've talked about why we are able to eliminate the denominators. Basically, we're multiplying the whole thing through by the denominator, so he's all gone. And I'm just going to solve what's left. It looks like in this case, this is just going to be a linear equation. So once again, let's get a little bit more room here. We will distribute. So if we do 12 times 15 and 12 times negative x on the left-hand side, we're going to have a 180 minus 12x. And if we distribute on the other side, we'll have 8 times 15 and 8 times x. So we'll have there just a 120 plus 8x. Like we said, it's linear, so I'll just get all my x's to one side and swing my numbers to the other. I'll just show adding my x's to the right-hand side. And again, you can skip steps as you see fit, but I'm going to try to show everything here so that we all are on the same page. So we have 20 x's on the right-hand side. I better move my numbers over to the left-hand side now. So we'll subtract 120 on both sides. And now we have 60 on the left equaling 20x on the right. So dividing both sides by 20, our x value here is going to be 3. Alright, so we've solved the problem. Now we better make sure our answer makes sense in the context. So kind of going back to some of our earlier stages, we were letting x stand for the rate of the current. So in this problem, we just found the x value is 3. Therefore, the rate of the current is 3 miles per hour. So our final solution to this problem would be the rate of the current is 3 miles per hour. And that seems pretty logical. Obviously, a positive answer makes sense here, and it's not too fast nor too slow. So hopefully that helps. These ones require a little bit of practice, but hopefully the box setup helps as well.